Hi guys, welcome back to Data Every Day. Today we're looking at a data set of best-selling books from 2009 to 2019 from Amazon. And we're going to try to use the title of the book, the author of the book, user rating, number of reviews, and price and year to try to predict whether the book is nonfiction or fiction. Alright, so let's get started. I have the task for today. Given data about Amazon's top 50 best-selling books, let's try to predict the genre of a given book. And I should probably include from 2009 to 2019, since it's not just 50 books we're dealing with here. Alright, I have imported a few libraries we'll be using, NumPy and Pandas, to deal with the data. We'll be using regular expressions, the stop words from Natural Language Toolkit. We'll use the tokenizer from keras.preprocessing.text and pad sequences from keras.preprocessing.sequence. And we'll also be using the standard scalar and train test split function from sklearn. For our model, we'll be using TensorFlow. So I've already imported those. Let's load in the data using pandas.readcsv. And we can grab the file path right over here, paste it in, and take a look. And you can see we have 7 total columns, so 6 of those are going to be our feature columns. And genre is going to be what we're trying to predict. Let's take a closer look with data.info. And you can see we have 550 total rows, right? And there are no null values in the dataset. Each column has 550 non-null values. Additionally, you can see we have 3 object columns, the first 2 being name and author, and last being the genre, which we're trying to predict. So we'll have to encode those in some way. So I'm going to start by dealing with a name. So the way I'm going to deal with this model, the way I'm going to build it, it's going to have 2 inputs. And basically, one input is going to be the names, and I'm going to embed them in a high-dimensional vector space to encode each one as a vector in a space with a dimension of my choosing. So, sorry, I may have misspoke. Not each name, each word in the name will be encoded as a vector. So that way I can feed in a sequence of words, and the model will be able to recognize each word as a vector, and then perform, train the weights as we need, because now they'll be in numeric form. So for the rest of the features, I'm going to just apply standard procedures. I'll probably one-hot encode the author column. I will change this to a binary 0 or 1. This is the label column here. But let's deal with the names first. So, stop words is, you can take a look at that. You can see it's from it's a word list corpus reader. This isn't actually giving us too much useful information, but basically stop words is it's a list. Actually, let me see. Can I load one in? We can do stop words equals stop words dot words, and we specify the language. Oh, I did not put equals. Alright, and let's take a look at stop words. You can see it's just a list of stop words. And so basically what this is they're words in possibly in our titles. This is just a list of words in English that offer very little information. They're not useful to include in the sequences. So what we can do is we can filter the sequences and remove any stop words. So let's create this function, process name. It's going to take in a name, so a given name. It will be one of these. And we'll start by removing digits from the name. So regular expressions.sub for substitute, And we'll specify regex, and then something to replace it with, and we're going to do this to name. So what we'll do is just say any digit character. So \d means any digit character, any number of times, one time or more. That's what this means. We will replace with a space. So this is just removing numbers. Then we'll split it. Name.split. So this will split on white space. So it will become a list. And then what we'll do is we'll join it back together on spaces. But we're not joining name. We're actually going to join a list comprehension that generates words for each word in name if word is not in stop words. So what this is doing is just, it's going to split it into a list and then bring it back into a string again, but only but removing any stop words in the process. And then we can return name. Alright, so if we wanted to process a given name, let's say we wanted this one, 10-day green smoothie cleanse. We can apply that to name, and you can see it has removed the 10 and also removed any stop words. In this case there are no stop words, so you don't have to worry about it. Alright, so why don't I process the whole column? And I'm going to take it out of the data frame right now. I'm going to make I'm just going to call it names. It's going to be so data sub name dot apply process name. So this will just apply for each row. It's going to apply process name and then save that in names. If we want to look at that, names will now look like this. So you can see all the numbers have been stripped, and additionally stop words have been removed. So here this originally said how to stop, now it just says how stop. Okay. Now what I want to do is encode this as a sequence of integers. So for that I'm going to need the length, basically the okay, let's see. So I want to know the length of the longest length of a sequence here. So what I'm going to do is I'm going to do names.apply a lambda function. It's going to take a name and it's going to return the length of name.split. So that will be, for example, this says 4. The length of 0 is 4 because there's 4 words. Basically what this means. Here is 5, here is 12. You can see it's basically just giving us the length of each example in words. And let's take the max of that. So numpy.max. So the longest title is 20 words long. So I'm going to call this max sequence length. Alright, and now we can create a tokenizer from keras.preprocessing.text, and it's going to we're going to fit the tokenizer, so fit on texts. We're fitting it to names. So here's names, and we're going, basically what this is going to do, this is going to find each unique word, and it actually is going to run each sequence through a series of filters first, and basically it's going to remove any characters that are not like word characters, any parentheses it will remove, any anything, that any colons will be gone, and then it will find it will find each word. Sorry, it will create a tally, like a running count of each word, and it will assign a unique integer to each word based on how frequently the word appears. So the most frequent word will be assigned to 1, the second most frequent word will be assigned to 2, and so on. And so from that, we can get a vocab length the length of all the words, which will be tokenizer.wordindex. This is tokenizer.wordindex. If I just run this, if I fit it, and I look at the word index, these are the most common words. The most common word, the second most common word, the third most common word, and you see they've been mapped to unique integers. However, there is one more, like because this starts at 1, the 0 is actually reserved for padding. So we're going to pad the sequences with zeros. So when we get the vocab length, we'll take the length of tokenizer.wordindex, but we'll add 1 for the 0. And let's print that. So vocabulary length. Alright, and we have 1160 unique words. Okay, so now what I'll do is I will use tokenizer.texts texts to sequences on names, and that will basically just transform the sequences that we have like this. It will transform them into numerical sequences using the word index. And when we're done, so if I just run this and I take a look at names now, you can see each one of these has been converted to these, and you can also notice that a novel has only 2 words. That's because it has been applied, it's been run through a series of filters, and it's been identified as just 2 words. Alright, and now we're going to pad it. So names equals pad sequences. This is from keras.preprocessing.sequence. We're going to pad sequences on names. We're going to set the maximum length of a sequence to max sequence length. So this will pad up to max sequence length if we have a shorter one. So I think our max sequence length was 20. So for example, this one only has 2, so it will be converted to a sequence of length 20 with zeros in all the other 18 spots. And that will happen for all of these. If we did have something that was over 20, it would be truncated down to 20. But since we are using the maximum length, we should not have a problem with that. And let's see. You know, I wonder if we could get the max sequence length here, because before, when we got the max sequence length, we were doing it to this sort of like less processed version. But what if we just get the maximum one of these? So if I did a see, I don't think we can apply. Oh, but we can map. So we'll map a function that will return the length of x, and we'll map that to names, and we'll get a list, and we'll take the max. Also 20. Okay, so we don't have to worry. But this would be a way to get the maximum sequence in this case. Do we use max sequence length here? No. We could specify the number of words in the tokenizer argument, but I think we're good to go. Here, why don't I actually just bring this down? I like this better. Let's take the, I'll call this name. And then I'll grab this and I'll just put this in here. Okay. So now we can pad the sequences. I actually didn't pad it yet. Let me pad the sequences after this. You'll see that now we pad the sequences using this max sequence length. And actually, let me specify padding equals post. So I want I mean, it doesn't matter so much, but padding normally will put the zeros at the beginning of the sequence. if I specify padding post, it'll put the padding at the end of the sequence. Alright, so I'll run through, and now you can see that the original sequences, this one was originally 2.9, is now 2.9.0.0.0.0 18 times, so that each sequence is of length 20. And now that we have this names, that it's ready to go into our model, we can now just drop the original name column from our dataset. Alright, and now let's start encoding the other features. So let's take another look at data. We don't have the name column anymore. We have this nice processed names NumPy array. But for the rest of them, we only have to do three steps, I'd say. One is let's convert the genre column into zeros and ones. Let's one-hot encode the authors, and then let's scale the data. So let's do that. Let's start by converting genre into zeros and ones. So what we can do is create a dictionary called genre mapping that's going to map nonfiction to 0 and map fiction to 1. And then all we have to do is say data subgenre dot replace genre mapping, and that will do all the work for us. So that's our new column. If we look at data again, you can see genre is now zeros and ones. Fantastic. Alright, next I want to know the length of the unique values in author. I want to know how many unique authors we're dealing with, because if it's too many, I might consider I'll probably one-hot encode it either way, since we have not too many examples here. But I want to try to avoid having just like way too many columns, but I'm pretty sure we'll be fine. I just want to make sure data sub author dot unique. We'll take the length of that, and why don't I print total, or actually number of unique authors. Alright, we have 248 unique authors, so that we'll add 248 new columns onto our data. That's perfectly fine. So we'll create this function one-hot encode. It's going to take in a data frame, a column, and a prefix. And we'll start by creating a copy of our data frame. Then we will we'll create a dummies data frame that will be pandas.getDummies df subcolumn, and with the prefix as we specified. And pandas.getDummies, I'll just quickly grab that, put it here. Let's say we wanted to get the dummies for author, and we'll have no prefix for now. You can see it takes each unique author, creates a new column out of it, and then one-hot encodes each example accordingly. So I can't actually see here. Why don't I try year? Yeah, this you can see. So each unique year in this case. So example 0 has a 1 for 2016. That's because example 0, the year is 2016. Also, we could put a prefix, y for year. That will just add a prefix to the name, and it's a good practice to keep a prefix on your one-hot columns. So here I'm creating dummies for a column, which in this case will be the authors. We'll specify the prefix. Then we will concatenate with pandas.concat the original data frame and the dummies data frame along the column axis. And when we're done, we will drop the original column from which we created the dummies. And then we can return the data frame. Alright, so what I'll do is I will just one-hot encode data. So data equals one-hot encode data, author, and then how about auth for prefix. So if we look at data now, we no longer have the original author column. We have all these different auth columns. There's actually 253 columns here. Each one is just a one-hot vector. Sorry, I didn't phrase that right. Each of these columns contains only 1, 1 for a given example. Okay, so let's split and scale the data. So y is going to be what we're trying to predict, and that's going to be data subgenre dot copy. So we're making a deep copy of the genre column. And then x equals data dot drop genre from axis 1 dot copy. So that's just going to be everything except the genre column. Alright, so x looks like this currently, and we want, these are all our features. We want to scale it so that each column has mean 0 and variance 1. So to do that, we'll just create a scalar object from, there's a standard scalar from sklearn, and we say x equals scalar dot fit transform x. So x will now look like this. It's no longer a data frame, and I could turn it back into a data frame even though it's lost the column names. You can see we have the same 252 columns as before, but each column is now centered at 0 and has unit variance. Now we will split them into train and test sets. And because we have this other where is it? Names, right? Oh, it's over here. This names that we got before is actually very useful. We have to make sure we split x and names the same way. So x is our other features, right? But names is also valuable information. So I'm going to split names along with x and y. So names train, names test, x train, x test, y train, y test is equal to train test split names x, y with a train size of 70% and a random state, let's say 100. Alright, so this will create 6 different sets of our data. A train and test set for names, a train and test set for x, a train and test set for y. So if we look at the length of names train is 385, and the length of x train is also 385. So you can see they've been split so that their indices match up, and we can use them together as inputs. Alright, so modeling / training. So let's get the shape of names and the shape of x. So we have 20 vectors of length 20 for our names, and vectors of length 252 for our x. So when we create our model, let's start with name features. We're going to create a name input layer. It's going to be tf.keras.input. And let's specify the shape here. It's just going to be the shape of a single vector from our names. So it's going to be a vector of length 20. Then for our embedding dimension, embedding layer. So tf.keras.layers.embedding. So the embedding layer is awesome. Basically, it's going to take the sequences, right? Names looks like this, right? It's going to send each one of these unique integers to a vector in a space with a dimension of our choosing. So let's actually choose the dimension. Embedding dimension. 64 seems to work well for this model. What that means basically is, alright, so there's multiple ways we could encode these numbers. If you recall, I believe our vocab length was 1160. Right. So if we wanted to one-hot encode these, which is perfectly doable, each vector to represent a single one of these would be of length 1160, which is just a lot of columns. And it makes more sense to use what's called a dense encoding. So one-hot encoding is called a sparse encoding because there's so many zeros. A dense encoding is what we're doing here, which is we're taking each word and sending it to a vector of length 64, but in such a way that makes sense. And what I mean by makes sense is the model is actually going to learn where to put the vectors. It's going to learn where to put words together so that the loss is minimized. And that's what the embedding layer does. So it takes in an input dimension, which is the vocabulary length, vocab length. It takes in an output dimension, which is the embedding length, embedding dimension. So we're taking in vectors of length 1160. We get like one hot vectors, right? And we're converting it to vectors of length 64 in 64-dimensional vector space. And then we also need an input length, which is going to be our max sequence length, which is 20. Alright, why don't we just give these names as we go. So we'll call this, we'll call it name embedding. And we'll also give this one a name, name input. Okay, we're going to pass in name input to embedding. And we will flatten that. So if I took a look at the shape, print embedding.shape, you can see it's basically 20. It's 64. How do I say this? So for a given sequence, right? It has 20 words in the sequence, whether those be zeros or not, but each word has now been embedded in 64-dimensional space. So it's actually a matrix of 20 by 64. So it started as just a list, a sequence of length 20, and then each one of those numbers has been converted to a 64 long vector. So this is what the shape looks like, and if we want to flatten it, that's what we'll do next. So we'll call it name flatten. Why not? It's going to be tf.keras.layers.flatten, and we'll give it a name. We're going to pass in embedding to this, and then let's take a look at the shape. So name flatten.shape. You can see it's basically all of those vectors stacked on top of each other have just been flattened into a single vector of length 1280. So I believe that's just 20 times 64, right? Correct. Alright, so this is basically all of the data, all of the information in our name column encoded as a single vector. And with that, we can actually include that in our final prediction. So let's remove this, and now let's move on to the other features. So now we're dealing with X, right? So I'll call it other input, and that's going to be another input layer, but the shape here is going to be the length of X, of a vector in X, which is 252. So 252 columns. Let's give this a name as well. Call it other input. And then we're going to just apply a simple two hidden layer neural network to this one. So we'll call hidden 1 tf.keras.layers.dense. 256 activations seem to work very well when I was testing out earlier. So we're passing in other input to this hidden layer. And we have another hidden layer, also dense layer, with 256 activations and a ReLU activation function. And here we pass in hidden 1. Alright, so now we actually have, basically it's an output from the name inputs and an output from the other inputs. And let me just give these names as well. Call it dense 1 or other dense 1. Like this, other dense 2. Okay, so these are our outputs from the other features. These are our outputs from the name features. So what I'll do is concatenate those together and make our predictions. Okay, so I can create a concatenate layer called concat, tf.keras.layers.concatenate, and it's just going to concatenate name flatten and hidden 2. So it's taking this one long vector with all our name data, all our name information, and this 256 length vector with all of our other information. And it's pasting them together, concatenating them together, and then we're going to have a final output, which is tf.keras.layers.dense with a single value and sigmoid activation. Let's also give it a name, output, and let's call this one concat or concatenate. And basically, this is going to be our probability estimate for whether a book is fiction or not. So a high value near 1 will be assuming the book is fiction, and a value close to 0 will mean the book is nonfiction. Alright, and then we'll create a model from that. Model equals tf.keras.model. So for the inputs, we're going to pass in name input and other input. And the outputs, we're just going to pass in the single outputs here. Alright, then let's print a summary of the model. And we'll also use tf.keras.utils.plotModel to see how the model looks. And I must have not passed something in here. Right, we didn't pass something into the outputs. Concat should go into the outputs. Okay, and this is what it looks like. You can see why I named them. Now we can see this nicely. So the name inputs come in, and the other inputs come in separately. The name inputs get embedded and flattened, and the other inputs get run through a simple two-layer neural network. Then the results get concatenated together, and we have another dense layer to get the final prediction for the positive class. Alright, and why don't we already, okay, yeah. So now let's compile the model. We can use an atom optimizer, binary cross entropy, loss, and we'll use two metrics, accuracy and area under the ROC curve. tf.keras.metrics.auc, name is AUC. Alright, then we will declare batch size 32, and we'll train for 100 epochs because I'm going to use early stopping. So we'll store our model's fit history in history, and then for inputs we're going to pass in names train and x train. Remember, we split both names and x. And then our labels will be y train. We'll include a validation split of about 12%. We will have batch size and epochs. Whoops. Given by how we already wrote them above. And then we will include a callback function. So it's going to be tf.keras.callbacks.earlystopping. And this allows us to automatically stop the model when a certain loss or metric goes down. When the model stops improving, we're going to stop the training and restore the weights from the best epoch. So we're going to monitor, this is the validation loss. So essentially when validation loss starts to go back up, we're going to stop the model. And we'll give it a patience of 3, so we'll allow 3 epochs to pass without improvement before we stop the model. And we'll also enable restore best weights, which will restore the best weights from the best epoch after we've stopped training. All right, and let's run that. So there it goes, and you can see it's stopped after 8 epochs. Let's evaluate the model. So just write results, and we're going to pass in names test and x test, and for labels we'll have y test. And you can see we have an accuracy of 86% and a AUC of 0.93. And because we have such little data, there's a bit of stochasticity here. Let's rerun it, see if we can get a better result. And now we're up to 90%. So yeah, it's a pretty good model. I think maybe there's some more things we could do to improve it, but I think we'll stop the video there for today. Thank you so much for watching. I hope you enjoyed the video. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. Thanks again for watching. I'll see you guys tomorrow. Have a fantastic day.